So I was like, in that scenario, okay, I'm just gonna write that off of my checklist. But I was gonna forget everything else.
Perfect fractions? Yeah, so this is pretty much, you want to yeah. So we pretty much looked at some of these integrals, like constant per liter, things like that. And then when we actually start getting perfect fractions, which led me to this, and then a big stick that I different.
Oh, as you get there, okay. Yeah, I need to watch this. The like,
Like, I don't think you can do, I have no idea, it was a spiral going on.
I know. It's weird, I was on the side, but my ski instructor forgot to teach me how to stop. It was the whole family, I was just, you get on the straight line, and then the other side. It's like something to be a bike.
yeah, I see. Thank you.
Once I fell down,
Yeah, yeah, man.
Okay, shall we? So we're going to finish up 6.3 today. We might actually carry it a little bit into next class. I'm trusting everyone had an opportunity now to finish 6.2 homework, partial fractions. So
6.2 or 6.3?
6.2.
Oh.
6.2, right?
6.2
6.2 is partial fractions in trig sub. I'm sorry. What the hell am I talking about right now?
6.3 is partial
Yeah,
fraction.
I know. Yeah, what's coming out of my mouth is not what I mean. So if that helps.
Okay, so what?
So don't believe anything I say. No. 6.2, trig integrals and trig substitution, you should be done with now. Partial fractions, I told you to wait until we finish today. So in college algebra pre-cal, you talk about this thing called partial fraction decomposition. And I just want to do one quick example of what it is, and then we'll get into the problem. So if you're back in an algebra class and you're asked to combine these three rational expressions together, you have to find a common denominator and put them together, right? So you look at the denominators, x plus 3, x minus 1, and x squared minus 1, and you try and find a common denominator between them. And you should probably take note that this x squared minus 1 would become x plus 1 times x minus 1, right? So now you find like an LCD, right? LCD. And what would our LCD be here? What would our least common denominator be?
X plus 3,
X plus 3,
X plus 1.
x plus 1, and x minus 1. So we just need to make sure that we get this to appear in every single denominator, right? And so we just go in here and we start inserting ones next to everything, right? So on this first one, I have 2 over x plus 3, and I'm going to multiply that by what? What do I need down here?
You're going to need an X plus 1.
X plus 1, x minus 1, both on the top and bottom, right? X plus 1, x minus 1 over itself. Okay, and that will give us the denominator we need, right? And then we do that for the next one, minus 4 over x minus 1. So here we would have to insert the x plus 3 that we don't have. And we also have to insert what? The x plus 1, right? So we're basically taking this expression, we're multiplying that fraction by 1, and multiplying that fraction by 1, and then the last one, we're going to, what do we multiply this last one by?
X plus 3.
Just x plus 3. That's the only thing it's missing, right? So x plus 3 here. All right. And then we put them all together, right? And so we'll have a new denominator. The denominator will be the common denominator. I'm going to just do this up here. So that'll be our x plus 3 times x plus 1 times x minus 1. And then we have to put all the numerators together. So it'll be 2 times this, right? So 2 times x plus 1 times x minus 1. And then minus 4 times x plus 3 times x plus 1. Still more, right? Plus 3 x plus 3 times x plus 3. And then what we could do is we could actually multiply this together and distribute a 2 through, multiply this together, distribute a negative 4 through, and then just distribute the 3 through, right? And that would be kind of our final expression, right? That process of going from here to there is not partial fraction decomposition. Partial fraction decomposition is what? Going backwards. It's actually going from that back to this. Okay, so that's what you do in pre-cal college algebra. So we will be doing that today, and I'll try and remind you of how we went backwards. Okay, I'll try and remind you as we go. All right? But it's impossible for me to cover the entire topic of partial fraction decomposition today. I can't do it, right? That's usually in college algebra, you probably spend a week and a half on it, maybe, something like that. So we can't possibly try and relearn it today, but I'll do my best because I realize that students do forget things, as do I. All right, so I'm pretty excited about today because I have these like cookie cutter problems that I've been doing for years now, but yesterday in my office was a box, and in that box is this new edition, 3rd edition calculus by Briggs, some other authors. And so what we're going to do is I'm going to just open this up to the section on partial fractions. I'm going to let someone in class, I'm going to just let you all pick what problem we're going to do, okay? So we'll do something I've not done. That'll be fun, for me at least.
That's the new book that we got?
No, that's the publisher wants us to choose that book. So they always send us free copies, and for me it's good because it's just more problems to use. Okay, so let's go with this one because we started this one last class, didn't we? Right, we did? Or at least we said this is where we'll pick up. Okay, so do you remember the first step? Like if you're starting this problem, what would be kind of your first?
Check the powers.
Check the power. So you're thinking partial fractions right now. Okay, so if we're ready to think of partial fractions, the first step would be to compare the degree of the numerator and denominator. But let's back up even further. When you look at this problem, the first thing you want to do is make sure there's not something easier that you could do other than partial fractions. And one thing we could try is doing a basic U sub, because the denominator is cubic and the numerator is quadratic. So maybe the numerator is the derivative of the denominator, and maybe we're off by a constant, and that's not the case here, all right? So we are then going to go down the road of partial fractions. Is it obvious that we can rule out like trig sub? Is that obvious that you shouldn't even be thinking trig sub right now?
Right.
Okay. Also integration by parts. I don't think that looks like any integration by parts problem we ever did, right? So it's a rational function. Let's go with partial fractions. All right, so we compare the numerator and denominator. Here, the numerator's degree is 2, denominator is 3, so do we have to do long division? No. Do not have to do long division. So what do? We try and do partial fraction decomposition. Partial fraction decomposition. Okay, partial fraction decomposition on the expression. So what we're trying to do is take this big, nasty, rational function. Notice I'm not working with the integral right now. I'm just writing down the expression, the integrand, and I'm going to just act like I'm in college algebra / pre-cal right now. All right, so I'm trying to rip this thing apart. So what we do first is we factor the denominator, if possible. So can we factor the denominator?
We could factor out an
We could factor out an x. Okay, let's do that.
or yeah.
2x squared plus 3x minus 2, right? Okay, can we factor that any further?
We could do, yeah, we could probably.
This factors, okay? So let me go another line here. X squared plus 2x minus 1 over x times, what are the two factors that we get there? 2x minus 1? X plus 2. Okay, so obviously this is Cal 2. I expect everyone can factor a trinomial. Yes? Okay, I know I'm saying that, but I realize that that still might be a struggle for some people, but we continue. All right, so now what we do here, going back to this method that we learned, is we look at the denominator and we look at these factors and we discuss what type of factors they are. So this first factor, x, is what we call a linear factor because it's x to the first power. 2x minus 1 is also a linear factor. And x plus 2 is a linear factor. They're all like little linear expressions, right, individually. So what we have here are three distinct linear factors. What do I mean by distinct? That's what we're working with. What's the word distinct mean? Unique. They're not the same linear factors, right? So like if this would have been x times x plus 2 times x plus 2, then we would have had x plus 2 repeated, right? But none of these are repeated. They're the same, they're different linear factors. They're unique. So that's where the word distinct comes from. So we have three individual distinct linear factors. So the method that we learn is that we can then rewrite that expression as some number, which I'm going to call a, over the first distinct linear factor plus some number, b, over the second distinct linear factor, and then plus some other number, c, over our last distinct linear factor. Does that kind of look familiar? Yes. Now, maybe in your college algebra class, you used like a subscript 1, a subscript 2, a subscript 3, no? ABC? Okay. A lot of times when we're doing these in general, we use subscripts, and I talked about, you could run out of letters, so the rule of thumb is this. For each distinct linear factor you ever see, you're going to put some constant a over each of the distinct linear factors. Now let me go back up into the notes and show you that like mathematically set, like that same thing I just said, but mathematically. Where is it? So what if you have a rational function where you have your numerator as a polynomial, our numerator is x squared plus 2x minus 1, and our denominator is a bunch of distinct linear factors, right? Here we have our first distinct linear factor, second one, third one, fourth one. You end at the nth one, right? Yes, then what you're going to do is you're going to break this thing up, and we must find these constants, a1, 2, all the way out to a sub n, where you have each of those constants over each of the distinct linear factors. Here we have 3, so we only go ABC. Yes? Okay. So now the question is, what do we do now, right? Like, what was the process at this point once we have rewritten it this way? Anyone remember what you do next? You multiply this equation by the LCD. So this right here is our common denominator, right? Or this is our denominator that all three of these factors appear, right, in that denominator. So we're going to multiply both sides of this equation by the LCD. Okay, so I'm going to do that right now. Move this out of the way. Okay, so I multiply the left-hand side of this equation by x times 2x minus 1 times x plus 2. And whatever I do to one side of the equation, I have to do to the other side, right? So I'm going to try and do this, squeeze this in here. Is that a problem? It's like music. So, as we get there. Okay, so when I multiply this side by the LCD, it distributes through to each of these three terms, right? So I'm going to put x times 2x minus 1 times x plus 2 on that one, right? And then same thing here, x times 2x minus 1 times x plus 2 on this one, and then x times 2x minus 1 times x plus 2 on this last one, right? So every single term gets hit by the LCD. Yeah? On the left-hand side, what happens? Gone, gone, right? Everything's gone except the numerator. Okay, equals. Now over here, when we do this first multiplication right here, I have a common factor of x in the numerator and the denominator, right? So the x's go away, but I'm still left with the a and the 2x minus 1 and the x plus 2. So I'm going to write that down. A, and then 2x minus 1, and then x plus 2. And then here, same thing. We get one of the factors to go away. The x went away on the first one. Here, the 2x minus 1 goes away, right? So we are left with a b, and then x times x, and then times x plus 2. And then our last one, the x plus 2 goes away. So all you're left with is the c times the x times, bless you, times the 2x minus 1. All right. Remember, our goal was to figure out what A, B, and C are, right? Now, how do we do that from here?
Don't we have to, find a variable, which would be A, B, or C?
Yeah, we have to figure out what each one
So then
is.
we have to set x equal to a number, so we can go ahead and have those cancel out, right?
Yeah, so there's two methods to do this, all right? There's usually two standard methods. There's a short way and there's a long way, all right? We always want to use the short way if we can. And if it doesn't work, then we have to go to the long way. And I'm going to show you both ways, all right? Now, the long way will always work. The short way sometimes fails. So we'll see an example where the short way fails. It's going to work on this one, but let's do the short way first. So the short way goes like this. The short method, what you're going to do is you're going to choose a value of x. You're going to let x be a certain value, and you have to think about this. Let's say we're trying to figure out what a is, right? If we want to know what a is, I'd like to choose an x that would kill this entire expression out and this entire expression at the same time. So what value of x could you choose that would kill this and kill this but not kill this? X is 0, right? If x is 0, that's going to be a 0. That whole thing goes away. X is 0 here. That whole thing goes away. But since x by itself is not a factor here, right, this won't go away. So we're going to choose x to be 0 right now. Let x be 0. And now what we do is we rewrite this whole line, this whole equation. We rewrite it. Okay, so what does my left-hand side become? Just -1, right? So -1 equals, and then I have a. And now this is 2x minus 1, but x was 0, right? So what is that then? Just -1. And then what is x plus 2 if x is 0? Just 2, right? And then what can you tell me about everything else? It's all gone, right? That's why we chose x to be 0. And if you look at that equation, that is a linear equation in a. There's only one variable, right? You can solve for a over there? Okay, so let's solve for a. What's a? A is 1/2. So we know what a is now, right? Good. Now we're going to play the same game, and we're going to go figure out what b is. Any questions? Okay, so if we want to find b, so we let x equal 0 here. We were trying to find a, right? And now we're going to let x be what to find b? -2. What do y'all think?
Yes.
If I'm trying to find out what this, well, hold on.
Yeah, it'd be -2.
Well, -2 will kill this off, won't it?
Yes.
I want to keep this one here. So I want to be able to kill these two,
Okay.
right? 1/2. 1/2. So all you have to do is just take that expression, set it equal to 0, right? And that'll tell you x is 1/2. So I'm just going to replace every x I have with 1/2. And this is what we're going to be doing to find b. All right, we have to replace everything with 1/2. Here we go. 1/2 squared, right? 1/4. Okay, plus 2 times 1/2. 1 minus 1 must equal, and now this we know is going to be 0, right? That's the way we designed it. When we plug in 1/2 right there, 2 times 1/2, that's 1 minus 1, 0. That whole thing's gone. So is this one. But we still have to plug 1/2 in here. Bless you. So b times 1/2 times 1/2 plus 2. Understand? All right, so now let's just keep going with this. See, over here these ones cancel. So you just have a 1/4 on the left side equals, oh man, okay. So I have to, order of operations, I have to do this first, right? What's that? Leave it as a fraction.
That becomes
5 halves, and then you still have to multiply that times 1/2.
And that becomes 5/4.
5/4. So I'm going to write it this way. 5/4 times b is the left-hand side. And finally,
We can multiply by the reciprocal.
multiply by the reciprocal of 5/4 on both sides. So what do you wind up getting for b here? 1/5?
Yeah, so 1/5.
B is a 5th. Okay, we've got 2 of the 3 down, right? Now we need to go get C. Questions? Sure? Deb? Yeah? No questions or no, like, what's going on? You're okay? Yeah. All right. All right, so now we're going to get C, right? So to get C, this is where we should let the x be -2. And you could have done that and got C and then come back and got B. It's the order you do it is up to you. But I'm going to just do it right here. So now I'm going to let x be -2. That's going to help us find what C is. All right, so we got to replace all x's with -2. So here we're going to get -2 squared, 4. And then plus 2 times -2, which is going to be -4. And then -1 equals, and, well, I'll get rid of this. It's one of the drawbacks to working on like an 8-foot by 4-foot board, 5 feet, whatever. Okay, what happens to this? When x is 2, it's gone, right? It's gone. And then here we just need to replace the x's with -2. So C times -2, and then we have 2 times -2, and then -1. Left side is -1. Okay, what about all this? This right there, that's -5, right? And we're going to multiply that by -2, so we're going to get 10. 10C. So C is -1/10. So we know what A, B, and C are. All right, so let's summarize what we have so far. The original integral that we had, the original integral, can now be rewritten with the information we just found about A, B, and C. So remember, look back in your notes. I said A was on top of what? It was A over X, right? What's A for us? 1/2. So what's the way I write this? I'm going to write 1/2 over X. I realize I could just put the 2 on the bottom, but I'm going to do this on purpose. So that's A over X, right? And then I should have plus. Now it should be B over, I forgot. 2x minus 1. And B for us was 1/5, so I'm put 1/5 over 2x minus 1. And then finally we have c, which is -1/10 over that last factor, which was x plus 2, and then dx. So now take a step back. What would you rather integrate? This or this? Well, you can do these term by term, can't you? Because they're separated by addition. And this is a constant over a linear, constant over a linear, constant over a linear. And we know how to do those because that's what we did last class, right? All of these are going to turn into natural logs, all of them, when we integrate them. Now, what I'm going to do, maybe one more step, I'm going to pull the constants out, and maybe now you'll see why I just left them the way they were. Does that make sense? Instead of trying to like put this 2 down here and the 5 down here, I just pulled the constants out of the integrals, and I'm just going to do them one at a time. It's been a while since I pulled these sticks out. Herman. All right, what's the answer, Herman? And if you don't know, it's okay. Just say, I don't know. Whoa, there is no Herman. Herman usually sits there. He's not here. Okay. Salo? What's the antiderivative of this?
ln.
ln, so 1/2. 1/2 ln absolute value of x. Okay, right? Plus, keep going, Sala.
ln
ln
of 1 over 2x minus 1.
ln of just 2x minus 1. But we're missing something. What am I missing? I need a 1/2 out front. So go back to last class. This constant over linear, antiderivative constant over linear is ln of the bottom, but you always have to scale out. If there's a 2 here, we have to scale it. So there's actually a 1/2. That's why I left a space here. 1/2 natural log of that. And then we have minus 1/10. And this last one, do we have to scale? No, because it's 1. So natural log of absolute value of x plus 2 plus c. And we're done. I mean, you could put those together. Okay, that's 1/10, but otherwise we're there. Yeah? Okay, so that was the short method. The short method to get a, b, and c. All right? Now, I'd like to show you the long method to get a, b, and c on the same problem. All right? So let's go back to, well, are there any questions? I'm about to erase all this.
No.
Okay. So let's go back to where we were. We had gotten to a point where it was like x squared plus 2x minus 1 equals a times 2x minus 1 times x plus 2 plus b x times x plus 2 plus cx times 2x minus 1. Is that what we had? Go back and check. I think that's what we had. Remember when we were at this line? That's where I said long way or short way, right? So now the long way. The long way, the way that you know you have to do the long way is if you're trying to like kill off, like you know when we were trying to find a and we were trying to kill off the b and the c, so we just let x be 0. If you can't figure out a number that kills these two off, then you have to use the long way. And again, you'll see in an example that I do in a little while. There are times where you cannot kill these off. Or if you do kill these off, you actually wind up killing this off too. So there's no way to like isolate the a by itself. So in the event that that occurs, we have to do the long way. So here it is. We're just going to multiply all this out. We're just going to expand everything we see here. So we have x squared plus 2x minus 1 equals a times, now I'm going to do a FOIL there, right? Yes?
Is it possible that like you start the short method and then it eliminates one, and then when you keep going, then at one point you can't do it?
Yes. So the question was, is it possible that you could start with the short method and then maybe get one of the variables like a and then realize you can't get b or c? And so then you continue with the long?
Yeah.
Yes, that could happen. Yep. Yeah. All right, so I'm going to expand this. Let's see, that's 2x squared. Okay, what about my middle term?
It becomes 2a, it becomes,
3x?
Yeah.
Okay, so 3x and then minus 2. And then here, this one we can just distribute that through. Let's go bx squared plus 2bx. So I just did here to here. And notice the way I wrote that, I put the b's in front of the x's, because the b is like a number. And I actually put the 2 in front of the b in front of the x. I mean, mathematically, you can write multiplication any order you want, but that kind of looks right. Doesn't this look more natural, like the number than the big letter, right, which is a number, and then the variable? Okay, and then we have, what's this? How about I write this next one? Probably 2cx squared, and then this last one, minus cx. And I still need to distribute that a over there, right? So can I cheat and just go, like, erase my parentheses and put it in there? Is that all right? Okay, so this is going to be 2ax squared. And this one's going to be 3ax. And this last one is going to be minus 2a. Okay, now, what we're going to do next is we're going to collect like terms. So I'm going to get all my x squareds together. That has an x squared, that has an x squared, and that right there has an x squared. So if I were to rewrite this, this would now become x squared plus 2x minus 1 equals 2ax squared plus bx squared plus 2cx squared. And now, next to that, I'm going to put all my x terms together. And I think what I'll do is I'll circle my x terms, because I've already underlined. Those are my x terms, like that, right? Those are the things that have x. So I'm going to write those down, and I'll even do it in blue. You know, the blue doesn't really come out on camera, though. It still looks like the black marker. C plus 2bx, and then minus cx, right? Those are my x terms. And then finally, I'm going to get all my constants by themselves. So do I have any constants?
Just 2a.
Minus 2a. This right here is a constant, right? Minus 2 times a. Okay. Next step, now that I've collected like terms, is I'm going to factor out what they have in common. So these three terms all have what in common? X squared. So I'm going to pull an x squared out, but watch the way I pull it out. We normally factor things out the front, right? Like off the front side. I'm just going to factor it out the back side. So it's the same thing. It would still distribute through, right? And you'd still have the same thing. And then this next one, I'm going to factor out an x from the next two, but I'm going to factor it out the back side. Nope, I'm missing something there. What should be there? 2b minus c, and then x. And then this guy's sitting all by itself, minus 2a, right? Okay, the whole purpose of this exercise of expanding everything out, collecting like terms, and factoring things out is because what we're going to try and see now is that we have an equation, right? And equations have to be balanced. So whatever's on the left has to balance with what's on the right. So when I look at this expression, I can see that this left side has an x squared, and it has a coefficient of 1 on it, right? So whatever the coefficient is on this 1 needs to match what the coefficient on this x squared is. So I know that 2a plus b plus 2c has to be equal to 1, right? I also know that the coefficient on x, which is positive 2, must match the coefficient on x here, which is that, right? And then finally, negative 1 has to match whatever constant I have out here by itself. I have all three of those things have to be true at the same time, right? These things together have to be 1. These things together have to be 2. And this thing by itself has to be negative 1. And what that gives you is a system of equations. So I'm now going to write that system down. The first equation I have is 2a plus b plus 2c must equal 1. The second equation is 3a plus 2b minus c must equal 2. And then what's the last equation? Negative 2a must equal negative 1. There we go. And back in college algebra, we usually put a big brace out front. This would be referred to as a system of 3 equations and 3 unknowns. So how do you solve a system of 3 equations and 3 unknowns?
You'd have to do elimination.
You can do elimination, or substitution is probably not going to be very good, because when you get 3 and 3, that's when substitution starts to not be your preferred method. Elimination. Matrices would be a really nice way to attack this. Really nice. Yeah, for this particular one though, we know what A is just by looking at this, right? We know what A is. So we could go and solve this. Now let me take a quick poll here. How many of you all own a TI, Texas Instruments calculator? Not, can I borrow?
Yeah.
So not like this one, but more of like a graphing one. Does everyone have one? Do you have access to one, Solo? You think you have one? Okay, does anybody have something other than TI? Just that, okay. I think yours might do this, but I think it might, yeah. Yeah, I don't know if that will. Okay. I tell you what, next class, please bring, if you have one, bring your Texas Instrument graphing calculator. If you've got a Casio graphing calculator, bring it. I can try and help you. If you don't have one, I'm not saying go buy one, okay? What I'm going to do is next class, I'm going to show you all how to solve this on your calculator, and it'll make your life easier as you move along in other classes. Being able to solve systems of equations on your calculator is a good thing, all right? We have to do it by hand because we don't have the calculator, but fortunately, we do have that A is equal to a half, right? Okay, so I can just tell by this equation right here, A is equal to a half. And then what can I do?
Then you could substitute.
I can plug it back in for these two, right? So this first equation would now become what? If A is a half, that's really 2 times a half, that's really 1, right? And I can subtract 1 on both sides. So that would tell me that B plus 2C equals 0. This one's not as nice. If I plug half into here for A, we get 3 halves plus what? 2B minus C must equal 2. Right? And then you could move this 3 halves to the other side, right? And now you have a system of what? 2 equations and 2 unknowns. And then you could do elimination or substitution. Now I'm not going to go through this, okay? Because we already have the answers. But you should, as an exercise for yourself, make sure you can get to the same answers we got earlier, solving that system. All right. Okay, what? That's 40 minutes? We did 1 problem? That's pretty good. But I showed you 2 methods, so that's why it took so long, right? All right, next example. All right, so we want to make sure there's not something easier for us to do. Basic U sub? No, because the only way we could do a U sub is if we let U be the top, because it's fourth degree. The derivative of fourth degree is third degree, but then the derivatives in the denominator, we don't like that. So,
What about long division?
well, yes, that would be our first step, because now we're thinking partial fractions. We're saying rational function. The power on top is bigger than the bottom, so now we have to start with long division.
Okay.
Okay, so that's where we're going to start. Long division, I'll do it right here. Okay, inside here goes the numerator. Already messed up. What'd I mess up there? Yeah, I don't have an x cubed, so I'm going to put myself a nice 0x cubed just for a placeholder. Minus 2x squared. I do have an x term. I do have a constant term. There we go, like that. And then on the outside goes the denominator, right? So x cubed minus x squared minus x plus 1. And now we start playing the game. So what do we multiply x cubed by to get x to the fourth? We need x. So we know this is going to be x. And then that x hits all those, right? Mm-hmm. So x to the fourth
Negative x to the third.
minus x cubed
Minus 2x.
minus just x squared.
Minus x squared, sorry.
And then plus x. And then we come through and change all the signs. All minuses become plus, and all the pluses become minuses. And then we add down. So we should get x cubed here minus x squared plus 3x plus 1. So everything comes down. Then 1, right?
Right.
To turn x cubed into x cubed, you multiply by 1. So plus 1. And then multiply everything by 1. That's going to be easy because I just rewrite it, right? So 1 multiplied by all that, you get the original divisor. And change the signs. You like these big old things I'm doing here? Isn't that fun? All right, add down again.
So I'll just give you 4x.
4x, that's it, huh?
Mm-hmm.
Okay.
Everything else.
4x. And this is where we stop the long division because you can't turn x cubed into 4x. So now what we do is we write the remainder, 4x, over the divisor, which is x cubed minus x squared minus x plus 1. And that is what we can replace our original integral with that expression. Right? Any questions?
Just integral from that.
Then we have to integrate that now. So here's where we are. The original integral is actually just the integral of x plus 1 plus 4x over x cubed minus x squared minus x plus 1 dx. And what's good about this is we can do these one at a time, right? So can we take the antiderivative of x? Sure. Antiderivative of 1? Yeah. Antiderivative of this? Yeah. Not. No. So we're kind of stuck now. Okay? But we've done the long division step, right? So we know that this right here, the power on top is going to be smaller than the bottom. Okay? So these two we're going to get an answer for. No more integral there. No more integral there. But this one we have not found the antiderivative of. So now this is kind of like just a new problem, right? And we just kind of start the procedure over. You know, we say, oh, this is a rational function. Degree of the top's smaller than the bottom. So we don't do long division. We now try to factor the bottom. Hopefully it factors. If it factors, then I can use partial fraction decomposition to do all that stuff with this, right? So I'm going to hit the pause button there. Oh, you know what? I have not drawn a pause button. I've been working on it my whole career, So there it is. It's impressive. It's impressive. We're coming back to that, okay? On the side here, I've got to do some partial fraction decomposition of 4x over x cubed minus x squared minus x plus 1. Okay, so no more integral. I'm just doing algebra now.
Factor x out.
You can't factor X.
We don't have an x in every term. Okay, so we have to go back and think about like what we learned when it came to factoring, right? GCF was always the first step. Do you have a greatest common factor that comes out of all of them? Here we don't.
Factor by grouping?
We count the number of terms, right? We have 4 terms. 4 terms means you should try grouping. Grouping doesn't always work, but that's what you should try if you have 4 terms. And we have 4 terms, right? So the way grouping works is you look at the first 2 terms right after the second term, right beside it, before this sign. You're going to split this up into 2, and then you're going to do little miniature GCFs on each of the 2 pieces. So if I were to ask us to rewrite this, the denominator here, just factoring a GCF out of here, they both have an x squared, right?
Right.
So I pull the x squared out, I'm left with what when I pull that out of there?
X minus 1.
X minus 1. And then I have to do a GCF on that also.
You can factor out a negative 1.
We could factor a negative 1 out. We don't have to factor a negative 1 out, but we need to because we need to have the same expression in parentheses here as we have here. So I need to realize a negative 1 has to come out of there, and that changes those 2 terms, right? So that negative x becomes positive x, the plus 1 becomes minus 1. And the whole key to grouping, the only time grouping will work is if what's here and here matches. Right? Okay. I've always thought this next step is a little weird. Let's go to the sticks. Nicholas? Is Nicholas here? Nicholas? How you doing, Nicholas?
Doing good, how are you?
Nick. Nicholas? Nick. Nick. Okay. It says Nicholas here, so. Nick, do you recall from grouping what this becomes?
Is it x squared minus 1?
X squared minus 1?
X minus 1 squared.
Just x minus 1.
Oh.
Just x minus 1. Okay. By show of hands, this is correct, okay? But by show of hands, how many of you would have done it that way versus how many of you would have written it this way? So, like this way. So how many of you would have done it this way, the way you learned grouping? Okay, and then everyone else would do it this way? Yeah? So why this way? I'm just curious.
Because you're factoring in GCF at both times.
Yeah, so this is kind of the big point, is that a lot of times students are taught to do grouping, and they're said, get these 2 things to match, right? And then your next line will just be this in parentheses, and then you just write whatever they match, just put that there also. And there's really not a lot of thought as to why. And I think it's important in Cal 2 for you to understand what you're doing in that step, because that is an algebraic step that needs to make sense up here. So I like to explain it this way. If I wrote down this, x squared times y minus 1 times y, then do we have a GCF? Do we have a greatest common factor there?
No.
Do they both have something in common?
Yes.
Y. Right? They both have a y? So you could pull a y out, couldn't you? So you pull a y out, and you're left with what?
X squared.
X squared minus 1. Yes? Okay, so that's exactly what we just did. But instead of y here, y is actually this entire expression. See, they both have something in common. And so what you're doing is you're pulling that y out, right? What's the y? This is the y that's sitting out in front. Does that make sense? You're factoring out the entire factor x minus 1. And that's why it sits in front of x squared minus 1. So these are both correct. I don't care which way you do it. But, you know, I don't like when... I didn't like it when I was a student. I was doing that. I didn't know why I was doing it, just other than I was told that's what it turns into. Okay? This is more like, okay, you're pulling the x minus 1 out. We continue. Right? and I've forgotten where we are. Okay, yeah, so we were trying to do this, right? And we've factored the denominator, almost factored. We're not completely done factoring because we need to realize, and I'm going to go with Nick's first answer to me, which I told you was correct, right? Just going to stick with that. If something goes wrong, we'll blame Nick at the end, okay? All right, so that's where we were, right? We have to be completely factored, and we are not completely factored because x squared minus 1 is a difference of squares. So now what we have is this. X plus 1 times x minus 1 times another x minus 1, right? Ah, okay. So now we're completely factored. And I'm going to write this one more time. Like that. All right, so this expression right here, 4x over x cubed minus x squared minus x plus 1, is equivalent to that expression right there, right? Now, we look at the denominator. We see a distinct linear factor, x plus 1. And then we see another distinct linear factor, but it's squared, which means it's repeated. Now, the way we deal with that is like this. So this goes back to partial fractions from college algebra. The way we deal with that is we say, all right, that equals, first, some number a over the first distinct linear factor plus some number b over the second distinct linear factor. But then we have to add to this another letter c over the distinct linear factor squared. So that's the procedure from pre-cal and college algebra. The way I like to look at it is this. Let me give you a different example underneath this, just slightly different. Like let's say that we had this. Okay? The method here would be distinct linear factor done with x plus 1. But I've got this thing repeated 4 times, right? Which means I'm going to need a b over x minus 1, a c over x minus 1 squared, plus a d over x minus 1 cubed, plus an e over x minus 1 to the 4th. So you got to keep on adding a constant over each linear factor, increasing the powers as you go until you get to that highest power. That make sense? So if it's linear, you need a constant over it, but then you keep on building up the powers on that until you get to the highest power that you see on the repeated factor. Questions? Okay, so fortunately for us, we're not doing this because then we would have 5 unknowns and a system of 5 equations, which would be why having a calculator to do it would be so much better. All right, but here we're going to have 3 unknowns, aren't we? Okay, so let's try and do this now. We need an LCD, right? Our LCD, Brandon. Okay, it's Rifa. Said it right too?
Yeah.
Yes. Getting it. All right, LCD on both sides, right? Okay, so what would the left side become? Just 4x? You feel comfortable just spelling out what the right side would be? Go ahead.
It would be xa
Mm-hmm.
bracket
Okay.
x minus 1 squared
Good.
plus b x minus 1, I mean x plus 1, and c
Plus c.
oh, I left an x minus 1.
Yeah, okay, so because your LCD has 2 of them, right? There's still going to be an x minus 1 here. And then here, x plus 1. Okay. Which one?
Bx plus 1, x minus 1?
No, because the LCD here is this, right? That's the LCD. You multiply that on the left and the right. When we do it right here, x plus 1 times x minus 1 squared, one of the x minus 1s goes away, but not both of them. All right. Are we all happy with that?
Just got like a quick question.
Yes.
For the A, B, and C's.
Mm-hmm.
I kind of remember, but don't really remember. But for like, if we need to put like CX plus some.
It's coming. It's coming. This is how we deal with linear factors. If we have quadratic factors on the bottom, then there's something else we do. Yep. So we're building up. I mean, we're slowly building up. Okay.
Just making sure I remember.
Yep. Right now, it's linear, constant over that linear. Linear repeated, constant over linear squared, constant over linear cubed, up until the highest power you see. We'll get to quadratic. I think my next example will hit that for us. Yep. All right, so here we go. Short way? You want to try the short method?
It won't work
It won't work? Why won't it work?
because all the time it comes
So if we try and do the short,
at least let x equal 1.
we need to let x be something. And let's try and get a, right? So if we try and get a, we need to be able to kill both of these off, right? Can you kill both of these off? You actually can. You actually can. You can let x be -1. And that'll kill this and this, right? So let's do that. We won't be able to get b and c, but we can get a. So let x be -1, right? So this becomes -4 equals a times -1 minus 2. Be careful there. -1 minus 2 is -2, right? Squared. So -1 minus 1 and then squared. That's that. And then here, 0. Here, 0. Y'all all right? What's going on? So this is -4 equals 4a. So a is -1. So a is -1. All right, now, great, we're all happy and ready to move on. Now we try and get b. So let's let x be, so we're trying to get b, right? Do y'all see the problem we have? B contains both factors that appear here and here. So if you're trying to get b by itself, you have to be able to kill this, right? So x has to be 1, but 1's going to kill this. And here, if you try and kill this, you let x be -1, well, you're going to kill this too, and you're not going to kill that. So there's just no way to get b without, yeah, it's just not happening, right? We can't get c. So how can we get c? We let x be 1. So why don't we go get c? Let's get as much as we can. Sir, what was your name again? Adam. Adam suggested this earlier. He's like, is it possible for us to use the short method and then wind up needing to do the long method, right? This is kind of that case. We're going to do the short method to get as much information as we can, and then we might wind up having to do the longer method. All right? So let's let x be -1. No, +1. +1. And then that will turn this into 4 equals, we know this is gone, right? We know this is gone, and this is going to become just 2c. So that means c is 2. We've got 2 of the 3 variables. We've got 2 of the 3. So how in the world do we go about getting b then? Yes, what do you got?
You can set b to, or x equal to any variable as long as it doesn't equal -1 or +1.
Yeah, we could basically play with x. Like we've kind of been like playing God here with x. Can I say that? I'm not offending anyone? Okay. We have control of x, all right? So as long as we use an x that isn't something we've used already and won't mess these things up, then we should be able to come up with an equation. That equation should have a, b, and c in it, and we already know what a and c are. So that will just leave b. So we're going to just pick x to be anything we want, other than -1, 1. So James, what do you want then?
0.
0 is a great choice because it kills a lot of, like the left side at least, right? That gives us 0 equals, okay, now this is not going to be 0, but what's a?
A is -1.
So -1